Hi, this is Mingyao. I'll be looking at how we set up Joule heating simulations in Ansys Workbench. There are a number of different packages that can do this. I'll be looking at starting with mechanical, Ansys CFD, and then Icepak. So Joule heating is this condition where when you run a current through a conductor, it generates heat. So it's a multiphysics problem that requires us to model both electrical conduction as well as heat transfer, and for fluid dynamics, thermal convection into fluid. So I'm starting with a pretty simple model here. You can see that I have a little conductor in the middle surrounded by an air box. So this is all inside the workbench environment. The first model I'll show is doing a thermoelectric simulation. Here's my model for a thermoelectric simulation, which is a conduction-based thermal analysis. We will not be needing our air box. Let's set the material for this part. We'll call it tungsten. Oh, tungsten. There you go. So there's a few tungsten alloys available in here. Let's go with a TA 10W. We can look at the material properties. Ansys has a pretty large material library now. So we have metal plasticity values, temperature dependent, thermal expansion coefficient, different SN curves for fatigue analysis, as well as isotropic resistivity and specific heat and thermal conductivity. So we have everything we need for this model. Let's look at the quick mesh. The basic standard mesh is very coarse for this, so I'm just going to go ahead and specify a mesh sizing on this body. We'll make it maybe 0.5 millimeter, which should give us pretty good resolution on this model. And now we set up the simulation. So we want both the thermal and the electrical characteristics. Let's make this a bit bigger. So I'm going to add some boundaries here. This will be my current, and I'll say, let's go to metric units here. We'll do 5 amps going into this terminal, and we'll set this terminal to have a voltage of 0. And this will tell us the resistance across this model, and it's doing thermal analysis. So we also need to be able to cool this down. So I'm going to select all of the surfaces and maybe deselect these parts. And we'll say there's a convection boundary on all of these areas. 5 watts per meter squared degrees Celsius is a typical setting for natural convection. So, and since we're not doing forced convection in this model, we're going to just guess at a number and see what type of results we can produce. So you can see within a couple minutes, from beginning to end here, we have a prediction of the temperature. So it's going to be 85 degrees Celsius. And that's how hot it heats up. We can look at the voltage. So the voltage drop across this conductor is about 56 millivolts, and we can also look at total current density and, let's say, Joule heating. So we can see where the heat has been generated. You can see it's kind of related to current density. So as the currents are going across these tight curves, we have some hot spots here where there's a large amount of Joule heating, and then it kind of stabilizes. We can turn the current density into vectors, which shows you the direction, and we can, get rid of the wireframe. You can change the vectors to solid vectors. We can adjust the sizes of the vectors. So there's a lot of basic pre-processing, post-processing capabilities to let us figure out how hot this little tungsten wire gets to. You can see, really easy to do a basic thermal electric analysis in Ansys Mechanical. The main challenge here is that the model is not we're not modeling the actual airflow itself, so we have to guess at what a convection coefficient is. In this case, I guess number 5, and you know, if I'm off by 1 or 2 watts, it's going to make a pretty big difference in the actual temperature I get. So let's do a CFD analysis now. So I'm going to use CFX. It has a pretty easy to use thermoelectric analysis capabilities, and here we can put in the air box, so we can actually blow air across our conductor. So same interface for meshing. I think one of the things I want to do is set the mesh to be the same on the conductor itself. So highlight meshing, we're going to put sizing in, and we're going to set a size of 0.5. One of the things that's nice to have in I'm going to hide all other bodies in CFD analysis is to have a decent boundary layer mesh. So we want to have an inflation on this body on these surfaces around there, and this will be typically I like to use first aspect ratio, so we'll do like a 20:1 aspect ratio, which means the thickness of that initial boundary layer mesh will be 1/20th of the size of that mesh. And let's do 10 layers. Looking at the mesh here, pretty coarse on the outside, but we care about the mesh around our tungsten wire. And you can see we have the tungsten wire well resolved. I can move this around a little bit so we can see it a little bit better here. Alright, you can see we have nice boundary layer meshing that resolves near wall flows, and this gives us accurate heat transfer coefficients and heat transfer calculations. So let's go ahead and run this CFD analysis. So this is Ansys CFX, which is one of our CFD packages. It's pretty easy to use, so I tend to use this when I can. It's right now everything is a single domain, so we need a new domain, and we'll call this our wire domain, and we'll say it's a solid, and it's so there's a part inside. So I think this is let's see. There you go, it's that piece. And we're going to do thermal energy, we'll do electromagnetics, turn on electric potential solver, and that's all we need to do. Oh, did I not specify a location? Here we go. Okay. Right now, since aluminum doesn't have material, and that it's not actually a new aluminum, so we're going to have to insert a new material. So CFX has a number of different materials available, but it really focuses on the fluid dynamics side. It doesn't have a wide range of solid materials available, really. So we're going to have to create a new material, which is pretty straightforward. It's called tungsten, and it's going to be a solid, and the material will be let's go ahead and copy the information out of Ansys Workbench. Now that we have defined tungsten, if I click on this button here, filter engineering data material, I see all the material properties we have for tungsten. So we have a density, which is in SI units, and we can mix and match units here. A specific heat capacity, and this is required for about 140, and I can change the unit globally if needed. Thermal conductivity, it's a solid, so there's no viscosity. There's a thermal conductivity here, which is 42, and there's a electromagnetic conductivity. So we have electromagnetic resistivity here, so we can put this in as an equation like this. Oh, I need to copy and paste. So we can always do 1 divided by, and the unit is ohm per meter. Oh, ohm meter. Oops. There you go. So the CFX will automatically do unit conversion for you, which is nice. And let's go ahead and change the wire from aluminum to tungsten, which has our electrical conductivity information. And now that's done. On the fluid dynamic side, let's check the models. It's going to be thermal energy. We're not going to worry about electromagnetics because we don't really want it to be conducting here. We have a turbulence model set, which looks fine. And now we can go ahead and set our boundaries. Looks like there's a heat transfer option here where it wants to make sure we have the right information. So clicking on the error message automatically takes you to the location to fix it. Okay, so let's go ahead and hide this and put in our electrical boundaries first. So this will be the current terminal. We're going to select this surface over here, and we want to put in a current. So it's in amps per inch squared. So we want to specify this will be 5 amps. But it's going to be, we need a kind of a area averaged. So we're going to divide this by the area at current terminal. Okay, and it takes it. So if you don't know these commands, you can right click. So the function will be area, and then the physical locator is current terminal. So that's what I did to specify that. And on this side, we'll call it voltage terminal. This will be over here. So we're setting up an apples to apples comparison, and the voltage will be 0. So or we can pick ground. Okay. So that's the wire setup. Now we want to set up the airflow. So we're going to have, by default, it's air at 25 C, which is fine. I can put in a inlet. So we're going to blow air on this side at 1 meter per second, 20 degrees Celsius. Then we're going to put in outlet. So if you have an inlet, you always need an outlet in CFD, otherwise air gets built up there and it's got nowhere to go. 0. And then the rest of the boundary is collected by this boundary condition thing. And we're going to set this to free slip wall. So we don't have no slip wall means there's zero flow, zero tangential velocity along the wall. Because I have fairly large mesh here, that's going to show up as some pretty large gradients. You know, 1 second it cannot move, then it can move. So we're going to let it slip by. And typically we should converge within 100 iterations, but let's do 200 just to be safe. And what we typically like to do is monitor the temperature, because we care about what the temperature is on our wire. So let's add a monitor point, and we're going to use an expression. So we're going to monitor max value of variables. Let's find temperature at locator 3D the wire. So we're going to try to track the maximum temperature on the wire as we run the simulation, and that's going to tell us when things stabilize. let's go ahead and go back to the workbench now that the CFD part is set up. We can do a quick analysis and see how hot it gets with 1 meter per hour wind. I probably don't need to do HPC, but let's just run off 4 cores. Okay, the simulation has completed. Let's go ahead and take a look at the results here. We can look at the wire surface, and I can plot the temperatures directly here. So it's at 58 degrees Rankine, so let's switch this to SI units. Or English engineering, let's see. Okay. Okay, custom, that's what we want. We have Celsius here. Okay, so it goes up to 53 degrees Celsius. Let's change the units so it's not in scientific notation. Okay, very similar patterns to our structural analysis. But because the convection is different, because we have forced convection here, the little wire is much cooler. You can do some cross-section plots on the YZ plane, and let's color it with pressure. To velocity. Do temperature maybe. You can see the heating effect of the wire and the air picking up the heat as it convects downwards. We can look at the velocity to show that this is a 26 millimeter per second. Maybe I used a strange inlet velocity here. Oh, 1 inch. let's do 1 meter per second. We'll run this again. So always check your units. Okay, let's look at our results again. It's recognized that there's some new results, so hopefully this will show temperature, and speed is just about 1 meter per second. Okay, let's take a look at the temperature again. So now it's only 37 degrees Celsius after the increased airflow. So airflow obviously has a huge impact on it. In addition to temperature, we can look at current density just like before. See the same kind of concentration of currents near the corners. And we can look at electric potential. So this shows you 56 millivolts of voltage drop. That's also very similar to the electrical results from our Ansys mechanical thermoelectric analysis. So that's an example of Ansys CFX. Let's go ahead and do this now in Ansys Fluent. Ansys Icepak. Let me close some of these things so that my computer can free up some memory. Okay, Icepak is a little bit different. We're going to have to duplicate our geometry because Icepak requires that we create an Icepak model for this for this analysis. Icepak analysis requires us to specify the type of geometry it is, and I'm going to use a very simple model to represent it. Okay, so this is our original geometry, and for Icepak we need to go to Ansys Space Claim and do some simplification. Now you can actually have the full CAD object, but it is much more efficient to model parts in Icepak as Icepak objects. This is because when it's all hexahedral elements, Ansys knows exactly how to mesh it most efficiently. And for the air box, I'm going to turn it into a bounding box because Icepak allows us to have overlapping models. So that's all I need to do to prepare this model for Icepak. Now I'm going to find an Icepak component system and start the analysis. Okay. The way Icepak works is that it automatically wraps a cabinet around the largest part, which is our enclosure. And really we just need the cabinet because our enclosure was meant to be our flow domain. So I'm going to delete this part. So now we just have a cabinet. We have to define our wire again, so we need to define a material. So let's call it tungsten. And it's a solid. We got go find our properties again. So let's pull this over, see if I can, okay, there we go. So the density is this value, and specific heat is 140, and thermal conductivity is 42.05. So that's tungsten. Tungsten will be these 4 components. You can see when I selected it highlights a little bit. To look at it a little bit better, we can go to select a solid highlight, so this way whenever I select something it gets highlighted. So these parts will all be tungsten, and it will be heated by Joule heating. There's a constant Joule heating or there's a variable version. So we're going to use the variable version and take my resistivity and put that into here and have it no temperature difference, no temperature variation. So basically the resistivity is a constant resistivity. And now we want to add the terminals. The terminals are these little battery signs. So we are going to move this to here. So this assigns a boundary condition here, and we're going to expand that. Okay. It's not going to add any power, but it'll add some current to it, 5 amps, and no voltage. And let's add another little battery here, and we're gonna move this to here, and I just click on this surface over and over again until it gets me the surface we want. Resize it so that it's the right size, and edit the voltage to 0. So exactly the same setup as before. We have 5 amps coming in here, 0 volts over here. We get a voltage drop across this wire. We want to adjust our cabinet so that the maximum side of Z is an opening and the minimum side is also an opening. We can do a grill too, but I will set an opening instead. The property for this will be in the Z axis, -1 meter per second wind, so it's going to be going that way. And on the other side, we're going to specify ambient static pressure. Okay. So you can see one of the benefits of Icepak is it does all of the meshing setup automatically. We can go through this quick problem setup wizard. So this will be an inlet-outlet force convection. I think we had it set at turbulence, so I'm going to set the same thing. We're going to ignore heating due to radiation for now. No solar radiation. Steady state. Under solution, typically we want to also, let's run a couple hundred iterations. And for parallel, we can use, let's say, 4 cores, the same as our other model. And typically we want to monitor the temperature, so I can select the part I want and create a monitor point. And it puts it in the middle, which is fine. And it creates a monitor point up here somewhere. Here. Okay, and we're monitoring the temperature, which is exactly what we want. So let's go ahead and run the simulation now. So Icepak automatically meshes this model. It's going to be a pretty coarse mesh. We could definitely tighten it up, but Icepak has some basic settings to make sure there's 3 elements through the thickness across the different parts. So it's not bad. It generally generates a mesh that's good enough to capture the temperature gradient across the different parts. Okay, obviously a problem here. I didn't let it run long enough to converge. So Icepak has a couple of different solvers. I probably should pick another solver. So I'll show you how I have to go about fixing that. Let's go to 500 iterations. And this time when I do solve, I'm going to use the coupled pressure velocity formulations. Probably should be on default. This makes it similar to the CFX solver that we just used previously. But let's go ahead and run this again. So amazing, right? How fast a different solver converges. Rather than running 150 iterations, 200 iterations, here it converges in 40 iterations. Shows you the power of the pressure velocity coupling. Let's take a look at the temperature on our wire. And display. So 33 degrees versus what was our CFD post result? So 33 degrees. We can also plot electric potential. So 56, 57 millivolts of potential drop. We can look at electric current density. The coarse mesh really didn't pick up the kind of the corner high current areas, so this is the area where more detailed analysis may have helped. And Joule heating density here shows you how much heat is being generated in the middle of the wire, which makes a lot of sense. So let's take a look at this, and just to compare the temperature. Okay, 37 degrees versus what's the temperature here? 33, I believe. Okay, so I know what. No, we did define tungsten. Okay, so it's probably a meshing issue, and if we look at plotted the wire here, and we show the mesh, you notice how much coarser it is. Right? So we can go in and set some settings on the mesh. We can do local meshing, edit object parameter, select the wire, and say define how many counts, and other things. But the idea of Icepak is to model very complex assemblies very quickly, and you can see it does make sure there's only 2 elements across the thickness. Okay. So I could really step up the mesh quite a bit here, even if I pick some global settings. Element in gap, minimum element on edge, that should be 3. Let's go ahead and generate this. This is only a 15,000 node mesh here. So I'll need to there's a coarse and normal one. There's a lot of other mesh controls that we can use to tighten up that mesh. But the idea here is I wanted to show you what we do in simulation to generate do a Joule heating analysis in Ansys Mechanical using conduction-based thermoelectric. We can do in our Ansys CFD product a full detailed CFD analysis that gives you a lot of control for meshing and kind of boundary layer modeling, advanced turbulence models, and for very large electronics cooling applications where you may have hundreds if not thousands of components, Icepak lets you set up these models super fast. So 3 different solutions, all can do Joule heating. Hopefully this was helpful. And if you like this video, please subscribe to our YouTube channel.